I'd like to tell you about work my lab is doing on quickly estimating all of the knowledge someone has at one moment in their life. One approach we've developed uses text embeddings, which are the representations that live inside of large language models and give them their superpowers. Essentially, text embeddings take any text and turn it into a feature vector, such that text passages or words that are conceptually related, like duck and goose, get mapped onto nearby feature vectors. Because these models are trained on huge text corpora that cover an incredibly broad range of content, text embeddings define a space for systematically organizing how different concepts relate. In one recent study, we used these sorts of text embeddings to follow how people's knowledge changed as they watched online course videos from the Khan Academy platform. We ran an experiment where participants took an initial quiz to get at their baseline knowledge. Then they watched a sequence of 2 course videos and took new quizzes after each video. If we look at sliding windows of the transcripts of each of the 2 videos, we can embed the text from each moment of each video in a shared space like this one. Each video's content is represented here as a blue or green line. We can also embed individual quiz questions within the same space. Each question is shown here as a dot. We can start to see the real power of this approach when we use it to estimate knowledge. For any coordinate in the embedding space, we can estimate what someone knows about the corresponding content by computing the weighted proportion of correctly answered questions, where the weights are proportional to how close each question's embedding is to that coordinate. In other words, we can estimate what the student knows about any arbitrary content in the space, even at locations that aren't near where the questions are. The map in the top left here shows what the average participant in our study knows, as estimated using the first quiz they took before watching either of the 2 videos. Because this 2D projection is invertible, we can also take any coordinate in this 2D plane and map it back onto the original feature space to get a sort of word cloud, like these. When we map out knowledge using each quiz in turn, we get a snapshot of what the average participant knew at different points in the experiment. After watching the first video in this sequence, we can see their knowledge about the content covered by that video bump up. Here's a difference map showing how their knowledge changed before versus after watching that video. We can continue this process of mapping out knowledge to watch knowledge change as they watch the next video too. We can make maps for individual people too. Here are maps from 20 different participants that we saw after they watched the first video in our training sequence. You can see that each person's map reflects their unique knowledge. Beyond mapping out knowledge for its own sake, we're also thinking about useful things we could do with these maps. For example, suppose these 2 people were having a conversation. If they're talking about the content in this region of the embedding space, we could imagine that their conversation might go pretty well since both of them have similar levels of knowledge. But in this region of the embedding space, there's a large difference in knowledge, so maybe they're not going to be able to communicate quite as effectively. On the other hand, maybe P1 here would be a good tutor for P2 since they're more knowledgeable about the highlighted content. In general, the way different people's knowledge maps align could tell us about how effectively or efficiently 2 people might be able to communicate. Beyond communication, these sorts of maps could be used as a general-purpose social networking tool. It can help you find a tutor whose knowledge overlaps sufficiently with yours that they'll be able to communicate effectively with you, but who is more expert in the relevant domain. Or we could use similar ideas to find people with complementary skills who might make a good team, or match up potential employees with careers. Having access to an interactive representation of everything you know could also help you learn more about yourself. It could drive automated tutors. It could drive recommendation systems to help point you to relevant content or experiences that could help you to meet your learning goals. And beyond these sorts of applied impacts, good knowledge and learning models that generalize across domains, people, and time will inform fields like cognitive theory, neuroscience, and even philosophical ideas about the fundamental nature of knowledge. We're excited about this work, and we think the sorts of ideas I've touched on here represent just the tip of the iceberg. We think this could transform how we think about what people know, how we educate, how we communicate, and maybe even how humans think. Thanks so much for listening, and thanks also to my awesome lab and the funding agencies that supported the work I've told you about today. We hope you'll check out our website if you'd like to learn more.